Hi, I'm here today to give a piece of a course lecture for a course I'm teaching this semester on second-order homogeneous linear differential equations, the specific method called reduction of order. It's a very special method, but I wanted to go through it in great detail, so I'm recording this piece for the class, but leaving it public so anyone can look if they want. This is a class called Math Methods for Physicists. As such, I'm more interested in answers than a similar course for math majors might be. A course in differential equations within a math department would spend a lot more time proving things rather than getting to the technique for the answer here. I am following a textbook we're using really closely in my presentation. That said, most textbooks for courses like mine do it really similarly. In fact, most math textbooks for pure math courses go through this technique about the same way. Now, there's a couple of little caveats before we get to this. We've seen that being a linear differential equation leads to a superposition principle, which is actually the reason that these are called linear differential equations. It's not because of the lack of square terms or things like that. It's because of the superposition principle and the linearity in that sense. What I mean by a superposition principle is that if I've got two solutions, f and g, then any simple constant times one plus any simple constant times the other, so any linear combination of the two, is also a solution. Of course, that's not the same for inhomogeneous or non-homogeneous differential equations. So you got to remember that we're restricting ourselves to this case. Reduction of order starts with having an equation, and the form that we're calling standard is up here. I've got the second derivative of y, which I'm using the prime notation for derivatives, alone. I've got a function of x possibly times y prime, and a function of x possibly times y. Homogeneous, so it equals 0. If we happen to know one solution, and sometimes there is one solution that's easy to get, or if you're in a class, maybe somebody tells you one solution. That would be a solution y1 that works in the equation. Because the equation's homogeneous, and because the product rule works for differentiation, you'll see, I think, why that's important in the next couple slides. There's a substitution we can always try. What we try is a new function y that's some function of x times the first solution. If we're going to make that substitution, we have to take the derivatives. y2 prime, we use the product rule, u prime y1 plus y1 prime u. And the second derivative has three terms, the middle one of which has that coefficient 2. You should be really familiar with this. That should sound easy. So we have to actually do that. We take the original form, we take that substitution, and we stick all that stuff in. And it's not pretty on the first line. I've made the substitution for y double prime there, the substitution for y prime there, the substitution for y. All I did was copy over these things, right? And then I reorganize these. I just shuffle around. This is 9th grade algebra at most. If I just carry those symbols around, I'm regrouping these, sorting by the order of u that appears, the order of derivative of u. So all the terms on the right have just the function u. The terms in that middle set of parentheses have u prime, the first derivative of u. And the term on the left is the single term with the second derivative of u. Now, the very simple thing I can do is look at that term on the right in parentheses. If I factor out that u, what's left inside, I gave it curly brackets now, is y1 substituted in the original equation. And the premise here was that we know y1 is a solution. And if y1 is a solution, that means the whole thing in curly brackets is 0. I just throw it out. All I did was throw it out. Rewrote this first part. I grouped those terms, factored out the u prime, and I noticed something. Now, I still have the y1 here, so it's not the same format, but if I divide by y1, this is now a first order linear differential equation in the variable u prime. A lot of books at this point would relabel this and call u prime v, and they'd say v prime plus same term in parentheses times v equals 0, just to make it clear and obvious that this is a first order linear differential equation. So that's something we know how to attack. In fact, in my class we already covered a couple of sessions ago a formulaic solution to the first order linear homogeneous differential equation. You can always do that. There's a formulaic way. In fact, for this one, if you notice, everything in that parentheses is just functions of x. There's no u, of course. That's a separable equation. There are other techniques too, but I'm going to treat it as a separable differential equation. That is, get all of the functions of x and dx on one side, and the v terms, the u prime terms, and the differential associated with that on the other side. So this is what it looks like. I just did the simple manipulation, and since I'm a physicist, not a mathematician, I can say multiply by dx. It's not forbidden for non-mathematicians to say such things. I can't necessarily do the integral I need to do. I don't know what these functions are, and that's one of my themes here, is that it's a formal solution. You get the format, you can't necessarily do it every time. But I copied that over and, quote, just integrate. Again, I don't know what the functions y1 or p are, so I can't actually do it now, and I may not be able to do it in general, but I know there's a solution based on that. This formal solution, I integrate the left side, I get the logarithm of u prime. Integrate the right side, well, I've got an integral. I solve that for u prime, and I get u prime is exponential negative that probably slightly messy integral, but it's a solution. So basically I've gotten all the pieces I need. U prime, of course, wasn't what I was looking for. I was looking for u, means I integrate it. So now I've got an integral of the exponential of another integral. It's just functions. You just go step by step and do it. In fact, I said I was looking for u, but that wasn't really what I was looking for. The complete solution to the original differential equation is this linear combination of y1 and y2. Not u. It's got y's in it. For some reason we knew y1. That's okay. Somebody told us, whatever. y2, I have this formal solution for, which is y1 times that function u. So I can rewrite this generic solution, factoring out a y1, and say it's a constant times y1, and this huge curly brackets, 1 plus another constant. These are different constants than the C1 and C2, but they cover the same space of solutions, times that integral of an exponential of another integral. That's it. I'm done. That's an answer. A few things to note. Having that solution is really a big deal. There might be caveats about where we divided by functions and whether the functions will be equal to 0. But in general, this means a solution exists, which is a huge deal for a mathematician. Reality, of course, you might not want to try to plug in that whole thing. You go step by step through this process. Sometimes you can't do the integral, you personally, but maybe someone can. And I put someone in quotes because I'm often referring people to Wolfram Alpha, tools like that, which can solve a lot of these integrals even if you can't do them yourself. In fact, sometimes the integrals can't be done analytically. There just aren't analytic solutions, but they can probably be done numerically, which again, tools like Wolfram Alpha, MATLAB, Mathematica can do. Because there is this formal solution, somebody can write computer code to do it, which is what the people who developed Mathematica, MATLAB did. They wrote in formal solutions in some sense. So those are some things to note about actually doing it. A little bit of an aside, you might have noticed some parallels in the method and the output. There's some real similarity to getting an orthogonal basis in linear algebra. Now this is just two functions, it's like a two-dimensional space. But a lot of textbooks actually go on at some length talking about spanning the solution space with these functions. And that's a good way to think about it. It's a way that can lead you to understanding more deeply what's going on and to how this generalizes into some other parts of solving differential equations, thinking of it as a linear algebra problem. In an almost deeper way, there might seem to be some similarity to what we're trying to do regarding factoring polynomials, or in fact numeric long division that you learned in 3rd grade or wherever, which is a special case of that kind of thing. Those may seem related in procedure. They actually are, not in a way that I'm going to get into in this 12-minute video. But it's interesting for you to try to think about how those things are related. You don't need it to solve them, but it's good for deeper understanding. Really, that's all there is to it. I don't honestly claim that it's easy or simple in any way. In fact, if you digested all of that, you may want to take a little breath for a while. Thank you, and goodbye.